invitado para que tengan un poco de antecedentes. Tras obtener su doctorado en el Instituto Tecnológico de Israel, el Dr. Decker dirigió a 50 investigadores en el desarrollo de baterías de alta temperatura en una empresa recién creada. En 2007, el Dr. Darío Decker cofundó Cell-Era, una joven empresa emergente en la que como vicepresidente del área de investigación y desarrollo dirigió a 15 investigadores para desarrollar la tecnología de celdas de combustible con membranas de intercambio aniónico, AEMFC por sus siglas en inglés, desde el desarrollo de los materiales hasta las primeras pilas del orden de kilowatts. En 2015 se incorporó al Instituto Tecnológico de Israel. Hoy es profesor titular en el departamento Watson de Ingeniería Química, donde actualmente dirige uno de los grupos de investigación más grandes del mundo que se dedica al desarrollo de la tecnología anteriormente ya mencionada. El profesor Decker estudia y desarrolla los materiales, componentes y procesos en las celdas de combustible con membranas de intercambio aniónico, electrocatalizadores de agua con membranas de intercambio aniónico también, electrocatalizadores para la oxidación de hidrógeno y la reducción de oxígeno, materiales ionoméricos, electrodos y celdas. Las publicaciones del profesor Decker abarcan desde los estudios fundamentales sobre los principales fenómenos y retos en los campos ya mencionados, involucrando estudios teóricos y experimentales, y su investigación está encaminada en nuevas direcciones que favorezcan el futuro de esas tecnologías. El profesor Decker tiene en su haber más de 100 artículos y 30 patentes sobre tecnologías de baterías y celdas de combustible. Actualmente gestiona numerosos apoyos gubernamentales de investigación en Israel, Europa y Estados Unidos. Por favor, recibamos al doctor Decker.
Buen día a todos. Gracias por la introducción. Unas pocas palabras en español, lo poco que puedo hablar. Muchas gracias por la invitación y la oportunidad. Es mi primera vez que estoy aquí en esta universidad. Entiendo que es muy importante y el departamento de química, que es muy conocido. Y en realidad la primera vez que estoy en México, por primera vez, para mí es muy especial. Así que de nuevo, muchas gracias por la invitación y esta oportunidad. Y por su bien, voy a pasar al inglés para que sea un poco más. Gracias. Should I, is that okay? ¿Pueden escucharme de atrás? Yo preferiría sin... Pero si hay algún problema con el sonido, díganme y yo uso mi programa. Israel.
Lo que pasa es que se está transmitiendo en YouTube y no escucha el audio. Eso.
Si pudiera usar el micrófono por la transmisión en línea.
Oh, okay. Yeah, I didn't think about that. Okay. Now it's better. That works. It's open.
Yeah.
Okay. Okay. Yeah. But somehow I have an issue. Cannot move the pages. It was before when we tried that. Maybe I would restart that. Okay, yeah, fine, thank you. So, sorry for that. So, this is my first time in Mexico, so I assume that many of you also don't know where we are in Israel and how small we are. We're really a very tiny
very tiny country, so I couldn't even compare with Mexico. You are like 100 times bigger than Israel. So this is our cities are small and our universities are small. So we have 7 universities. Technion is one of them. Just to show, to look at in the map, the only way you can see us is at the night. So then you see all these lights. And this is Israel. So this is Africa, Middle East here, and Europe here. So that's a very tiny country that we are trying to do our best in terms of education as well. So Technion was founded more than 100 years ago. I thought that Technion is a big university until I heard that you guys have 100,000 students. So we are really a very small university. We are ranked around 80, more or less, in the worldwide ranking in all the universities in the world. And this is the top university in terms of engineering and in terms of chemistry, physics, and mathematics in Israel. So in the past 10 years, Israel opened 2 new universities, 2 new campuses, one in the States. Together with Cornell, we founded a Cornell Tech in Manhattan. So that is already 10 years, I think, running. The campus is getting bigger and bigger, and that is a very good one. And the second one was like around 6 years ago, or 7 years ago, that we founded Technion Guangdong University in the south of China. So slowly Technion becomes much more a bigger presence in the world. And we are located in the north of Israel. So those are a few pictures in the north of Israel. So all Israel is near the Mediterranean. So we have a very nice beach and a very nice view. This is just a few minutes driving outside from the Technion campus. So what what I do since I joined like 7 years ago, so I started working with anion-exchange membranes, and with mainly at the beginning with the application of anion-exchange membrane fuel cells. So my hobby is electric vehicles, so I'm very focused on that. However, of course, we now work on many other technologies. So we develop catalysts, only PGM-free, so no platinum. Platinum-free catalysts, membranes, only anion-exchange membranes. So we develop from the monomers, polymers, and all the way to membranes and the application. We are very focused to applications, so we have a modeling of the cell or the fuel cell or the electrolyzer, and we have many collaborations. Unfortunately, Mexico not yet there, but I hope we will find some good collaborators here. All what I say normally that we do, so we do together with many collaborators around the world. So to start, for those who are not familiar, talking about the membrane, so an ion-exchange membrane is like a proton exchange membrane. So normally we work with hydrocarbons, but can be fluorinated. And we have cations fixed to the membrane, so that's the way that we have mobile anions, normally OH minus, but also any other anions that we can conduct. Now those functional groups, or those cations, can be inserted into the backbone of the polymer in different ways. So there are many ways that they can be inside or part of the backbone, like polyimidazolium, for instance. It can be like a side chain, and then the cation, that is to increase the mobility of the counteranion. Can be different positional multi-cations, like a branched, and can be, of course, a combination of all of them that we call hyper-branched. That this is less popular, but we can do also as well. Now, while we work with an ion exchange membrane at all, so there are many applications. Power generation, this is the first one and the most popular, meaning an ion exchange membrane fuel cells. But we started working a few years ago already, and today is very popular in Europe and Korea and Japan, starting also in the States, the hydrogen production, meaning an ion exchange membrane-based electrolyzers. You may not be aware, but also those ionic membranes can be used for artificial muscles that we take the advantage that we have the ionic part of the backbone, so then when we apply a different potential, we can have a distortion, and then with that distortion we can move things and we can create movements. Many other uses are less popular but started now being more and more investigated, like production of CO or production of fuels, meaning by means of CO2 reduction using the anion exchange membranes. I understand that you work a lot with redox flow batteries for energy storage, so then also we work an ion exchange membrane for this option, as well as, for instance, as a CO2 pumping, or as we sometimes call it, CO2 sequestration. So there are many, many applications, and this is the reason why we investigate and focus in my group on anion exchange membranes. The focus on the application in my case is mainly fuel cells. Again, we started a few years working with electrolyzers, and now we just now start working with redox flow batteries. But of course, we have many collaborators working redox flow batteries using our anion exchange membrane that we produce for them. Now, why we work at all with anion exchange membranes? There are much more mature options like Nafion that you know for proton conducting membranes or cation conducting membranes. So the main reason is that this is for fuel cell, but this is the reason that in all the electrochemical devices we change the proton exchange membrane for the anion exchange membrane, because in this way we can conduct OH minus or any other anion, and therefore the medium that we have is alkaline, and then the electrochemical reactions are different. When the electrochemical reactions are in alkaline system, we can afford to use catalysts or electrocatalysts that are not platinum, so we can go to very abundant and much more cheaper options, and that is the reason we use these membranes. So if you change, for instance, the platinum, and we are working with iron, nickel, cobalt, and many other metals, they're very affordable and very abundant. And the membrane, so if we do not need to withstand very low pH, we don't need very expensive fluorinated monomers, so we can work with hydrocarbon backbones, for instance. So that is much cheaper, much more available, and of course here we have like 3 orders of magnitude cheaper catalysts. So in principle, all the stacks that you have in the fuel cell or electrolyzer or even redox flow batteries, so that will be around 50% of cost reduction. That is significant cost reduction that can push these technologies forward and solve the main issue that we have, which is cost. I will not focus on redox flow batteries, however, from time to time, so I will say something about that. So those, for instance, reduction in cost and all challenges that we have for electrolyzers or for fuel cells. So we have different additional challenges, of course, but also additional advantages in an ion exchange membrane when we use for redox flow batteries, because if we have in alkalines and redox flow batteries, we have multi-cations and multi-anion systems, and of course those cations that are even +1, and of course if they are +2 or higher, they will not cross through the anion exchange membrane easily, at least. So then we don't have crossover, meaning the efficiency of some of the systems in redox flow batteries will be even higher. And that is some unique advantage of the anion exchange membranes for certain redox systems that you can get also, and we do not have any problem, for instance, on fuel cell and electrolyzer, but in the redox flow batteries, we enjoy those advantages. So, as I mentioned, the anion-exchange membrane is a very new technology, actually. I mean, the polymers exist for electrodialysis for many, many decades ago. However, those polymers and those membranes are completely different from other electrochemical devices that are much more severe in environments like fuel cells and electrolyzer and redox flow batteries. So we can say that just started investigation around 15 years ago when I founded my startup company that was here. Actually, it was just 3 groups in the world working on this type of membranes, and there was one company having kind of products in Japan and one company in Germany, but no more than that. And since then, this is for fuel cells. You can see all the anion-exchange membrane of fuel cells based on an anion-exchange membrane. That's the number of articles per year, so this is a really blooming technology. Most of the groups, most of the papers are in the States and in China, and then also in Japan. I think that Israel, we are here. Of course, again, we are a very small country, but still in this type of technology, we have a great contribution. So thanks to those number of articles, you can see very quickly how the fuel cell performance, you can see here from voltage versus current density. Since the very beginning, we were talking about just a milliwatt per square centimeter or milliamp per square centimeter. And today, for the last few years, we're talking about a few watts per square centimeter and few amp per square centimeter, which is really an impressive learning curve that we have on an anion-exchange membrane for fuel cells. So that is really remarkable. Now, if fuel cell using an anion-exchange membrane is very young, so electrolyzer is even younger. Just a few groups you can see here in the past 10 years working, a few just articles you can see in red. We're not talking about hundreds of articles, but we're talking about tens of articles. But you can see that now is starting going up and more funding again coming from European community and from the States also coming. So we expect that the anion-exchange membrane-based water electrolyzer will be a very hot topic in the coming years. You can see just even in a few years, based on the normal liquid electrolyte water electrolysis, when we started working with an anion-exchange membrane, we have significantly improved also in performance for the electrolyzer working with an anion-exchange membrane. So that's one of the reasons why also we are sure, or I'm sure, that this technology will be really very popular in the coming years. Now, if you look at the why this progress in both fuel cells and electrolyzers, and lately also just now started on redox flow batteries, is because of the great advances that we have as a community in the anion-exchange membrane. So you can see just a few years ago in red you see I will not use anymore this, if you have some other that would be great, or maybe need more batteries, I don't know. I cannot see where I'm pointing. So in red you can see the points of the conductivity per anion exchange capacity of the membrane. So you can see in empty circles, you can see the PEM, or the proton exchange conductivity. So until a few years ago, the conductivity of an anion exchange membrane was relatively low. And then we understood how to make progress in this, and you can see on the right plot, you can see conductivity that we achieve in all the publications from different groups in the world, how that conductivity was improving during the years. And then today you can see many of those research. You can see conductivity of drugs, a conductivity of more than 100 millisiemens per centimeter. That better? Okay. Which is this one? This one? Thank you. So you can see here conductivity versus temperature, and here some line of 100 millisiemens per centimeter, which is the Nafion conductivity for proton conductivity. So you can see many examples, and there are more in the recent year of an ion exchange membrane that we have even more than 100 millisiemens per centimeter. And I do not see any intrinsic limitations, so I expect to have more and more advances on this. So thanks to this very high anion conductivity, specifically OH minus conductivity, but all other anions as well, so we could have this success and this really quick progress in fuel cells and in electrolyzers in the community. But this is not the end. We still have many, many more challenges. This is, for instance, from one review that we published last year based on an ion exchange membrane water electrolyzers. So those are the state-of-the-art parameters, and this is the target from the European community set for 2050. And we have many, many gaps here that we need to overcome, and all those that I mark in red meaning that we need better membranes, not just in the conductivity, but also in the stability and all other parameters in order to satisfy the demand that we have on the electrolyzers. Same we can have in the fuel cells for automotive or for maritime transportation, or we are talking now for buses and trains and airplanes. So we need better and better membranes, so we keep working on those membranes. So I will focus on two, this is a short talk, so I will focus only or mainly on two parameters. One is how is the effect of the CO2 to this anion exchange membrane, and the second, which is the measure, the number one, I would say, challenge, which is the stability in alkaline. So I will start with the CO2 effect. We work a lot at the Technion on this issue, and just for those who are not familiar, so what happens is when you have work for fuel cells, for instance, you have working on ambient air, so you have the CO2. CO2 dissolves in water and penetrates into the anion exchange membrane. So when you have an anion exchange membrane, well, that green is much better. That's a super laser pointer. I will take that one. Thank you. Wow, good. That's cool. Okay, so what happens is that when you have CO2 dissolves in water, and therefore you have not just OH minus, you have also bicarbonate anion and carbonate anion. Those anions are huge size and less mobile than as compared to the OH minus, and therefore the conductivity, the anion conductivity, when you have more and more carbonate, so reduces, and you can see it's like it can be like 5 times smaller. And if you have now an anion exchange membrane with conducting an anion that the conductivity is 5 times smaller, so what happens, for instance, when you have an electrochemical device like this fuel cell, if you operate here, the power that you have when you put CO2 or you switch from CO2 free air to ambient air that contains 400 ppm or more of CO2, you can see an immediately loss of power of around 1/3 of the power that you lose just because you have now bicarbonate or carbonates. And when we measure the diffusivities also, we can see consistent data. The diffusivity that we have inside an ion exchange membrane is always significantly higher than diffusivity that we have in the same membrane, but with bicarbonate form instead of OH minus form. So all these make this a challenge for the anion exchange membrane that is nothing to do, not a problem at all when you use, for instance, Nafion that you conduct protons. So what happens when we have a fuel cell, for instance, or similar devices, so instead of conducting OH minus, actually we have 3 different anions, the OH minus, the carbonate, and the bicarbonate. So we have working a lot in modeling, trying to see what is the real effect, what will happen, and how we can deal with this effect of the CO2 inside the device. And what we see here is the relative concentration of those anions at different conditions, different operating current densities of the device. So we found very interesting things. First of all, the bicarbonate is negligible when you operate a fuel cell device. So actually we have only two main anions, the bicarbonate and the hydroxide. And if we want to change the current density, let's say we work on high current density, we have significantly higher amount of OH minus. If we work with very low current density, we have significant amount of carbonate and almost no OH minus. That actually gave us an idea that we can use these membranes actually to take the advantage that they react with the CO2 in order to make what I show in the first slides, that we can have CO2 pumping. So we can use that to have CO2 in the cathode pumping through the membrane, working on a very, very low current density, and then pump the CO2. So we can use that as a CO2 concentration to clean the CO2 using electrochemical device, which will be much, much cheaper than any other solution that we can think today. So sometimes we can take advantage of those challenges that we have with these membranes. Another thing that we learn is that we need a new method to try to move this carbonate very fast. So we were thinking at the Technion and studying that for 2 years, how to study what we call the CO2 release. So we think about this very simplistic method. We started with a membrane that is exposed to the air. When you expose an ion-exchange membrane to the air, you have a bicarbonate form. So when the membrane is in bicarbonate form, we have the 4-electrode probe. We measure the conductivity. And here in the plot, we have the conductivity versus time of the test. At the very beginning, we have the membrane in bicarbonate form, so actually we measure the bicarbonate conductivity. And then we put all that into a closed chamber. We flow humid nitrogen, and we set the temperature and the relative humidity. And what we do is we make water splitting. We use these two electrodes, and we apply a current, and then we start splitting the water from the humidity of the nitrogen. And then we generate hydrogen in the cathode and oxygen in the anode. And the OH minus started getting inside the membrane and actually are like pushing the bicarbonate or exchanging the bicarbonate. And we reject the bicarbonate as a CO2 here in the anode. So from time to time, we keep measuring the conductivity. So you start seeing the conductivity goes up. And this is a clear indication that actually we have now some OH minus, that as I said before, they're much smaller, much more mobile, so the conductivity is much higher. We continue doing that, and you can see more and more OH minus, and then we keep from time to time measuring the conductivity until we reach this plateau. And this plateau we coin a new term, we call true OH minus conductivity. And the reason is that this is the full OH minus form of the membrane. So every time that we want to make this OH minus conductivity, normally what people do, put the membrane in 1 molar KOH, exchange the bicarbonate, and then you measure the conductivity, but you always have contamination of the bicarbonate there. But using this way, if we keep applying the current, we keep generating the OH minus and pushing the bicarbonate, so we can be sure that we have 100% of OH minus and not bicarbonate at all. We also follow by GC, and we saw that we do not see any more CO2, so that's another confirmation. And this is the real or true OH minus conductivity. So we measure that on more than 20 types of membranes, and we always saw that this true OH minus conductivity is much higher than what other researchers claim to have, and the reason is because we do not have any contamination. So although we were studying the conductivity properties, actually how to exchange the CO2, how to exchange the bicarbonate, for OH minus. We found a way first how to create a new device that we can clean the CO2 from the atmosphere. And second, we found a new method to actually measure the real true OH minus conductivity. So this is, of course, a measuring property of the anion-exchange membrane. Doesn't matter if you are going to use that for redox flow batteries, for muscles, or for other fuel cell or electrolyzer. This is the best way that we have today to measure the OH minus conductivity. Now the second challenge, as I mentioned, is the stability. So we have some main issue at the very beginning, that most of the anion-exchange membrane that we developed were not so stable in KOH, in alkaline solutions. That creates a real problem, because people at the very beginning thought that we will never be able to have an anion-exchange membrane. At the beginning was the conductivity issues very low, now it's higher, and then we start thinking that the stability is very bad. And the reason was that the functional groups that we had a few years ago were not so stable. So we always degrade during time in KOH solution, and therefore the conductivity actually reduces during time. And that's the reason why in the community, if you look, most of the papers on an anion-exchange membrane are focusing on developing new cations and testing the new cations in 1 molar KOH, or even a high temperature, or even a 6, or even a 10. There is one publication on 10 molar KOH, trying to accelerate the process and see the stability of these cations. So this is a paper just published a few months ago, and we actually review all the cations that we found in the literature. This paper has more than 1,000, I think like 3,000 citations. A really very good source of that you can learn about an anion-exchange membrane. We publish for water electrolyzer, but this is also very also informative for all other electrochemical devices. And there are more than 40 different cations, different type of chemistries that today we develop. And we also found all the chemical degradation mechanism for all those cations. So the bad news is that every cation have a degradation mechanism. There are no cations until today that are exempt for these degradation mechanisms in alkaline solutions. And the second bad news is that all, without getting into the details, but absolute all of the cations have one thing in common. The mechanism is that the OH minus attacks some point of the cation and then destroy the charge, and the charge is loosed. So the conductivity of the anion-exchange membrane will be lower and lower during time, during this degradation. And the bad news is that the attack of OH minus is bad, because we are talking about OH minus. We're talking about alkaline, even if we are talking about CO2 reduction device or redox flow battery device, fuel cell electrolyzer, all we have KOH, or we have alkaline, or we have OH minus being generated or consumed. And therefore, we have an intrinsic problem. So we need to understand that we always will have a degradation of these anion-exchange membranes due to the degradation of the cations, due to the presence of the OH minus. So what we can do is to study the mechanism of reaction and to try to see how we can lower the rate of degradation and how we can keep on protecting this mechanism specifically for each cation, so we can have more and more stable membranes. Because after all, the devices need to be, not to work forever. We need, if it is for automotive, we need 8,000 hours. If it is for electrolyzer, we need 20,000 hours, etc. So we need a limited time that we need to have stability. And if we can meet those targets, so that will be a good solution, or good enough solution. So that is the reason why the community was working very hard and testing, as I mentioned, more than 40 types of cations in different solution. This is one of colleague of mine in Max Planck in Germany, working with 6 molar, 160 degrees Celsius, very aggressive. And we found a cation called ASU, very, very stable. Another colleague of mine in Simon Fraser University in Canada, these very, very bulky midazolium type cations. You can see he found in 1 molar KOH, 80 degrees Celsius, 8,000 hours stability. And there are thousands of papers of many other cations that always were very stable in these solutions. And then the researchers use those cations, insert in the backbones. There are many backbones very stable in alkaline, and they put membranes, and you can see here how they measure the conductivity of the anion conductivity during time in those membranes. So there are many type of membranes that today, mainly in 1 molar KOH and 80 degrees Celsius, are very stable for, let's say, 1,000 hours or even more, with very low degree of degradation. However, when you put all those so-called stable membranes inside the device, those membranes are not stable. So this is a review, for instance, of all the it looks like a mess, but if you look at the number, so there are no tests more than 2,000 hours, and actually most of the fuel cell devices work a few hundred hours, and you see a huge decay, an important decay of voltage during time. And this is because the membrane is not stable. So the membranes were stable in 1 molar KOH in ex-situ test that we normally do, but when you put those membranes that are supposed to be stable in the environment of the fuel cell, they were not so stable. The same happened if you put those membranes in an ion exchange membrane water electrolyzers. Again, you can see those are all the data that we have today put in one plot, and you can see 500 degrees Celsius here, an increase in cell, meaning degradation, the opposite of the fuel cell. So all the devices, and there are almost no work on the stability of the redox flow battery of this membrane, but also in 1 molar KOH, so also will degrade when we have the device. So there is a huge gap, I would say, between what, for instance, papers from polymer chemists say that the membranes are very stable, and those are ex-situ stability tests, with the device for the electrochemist or chemical engineering they do in the fuel cell or electrolyzer, that the membrane inside those environments are not so stable. So at the Technion we were devoting really many resources and many years working, trying to explain why the membranes are stable ex-situ but not stable in situ in alkaline systems. And we finally understood by using numerical modeling. We developed the model especially to understand what is going on inside, because you cannot make all the measurements that you have when you have a fuel cell or redox flow battery. So in the modeling you can see or simulate what is going on inside the cell. And what we found, you have here, we simulate all the cell, and you can see here a plot of lambda. Lambda is the hydration number. Hydration number is the number of water molecules around the OH minus per location. So we have the anode, we have the cathode, and the anion exchange membrane in the middle. So first of all, you can see a lot of water in the anode and low water in the cathode. Low water in the anode, we are around lambda of 20. So you have 20 water molecules around the OH minus. The OH minus is very well solvated, and therefore very well stable, as you will see later. And this amount of water is very reasonable. So if you think that in the electrochemical reaction, actually we generate when we oxidize the hydrogen, we generate water. So that's very reasonable. Now in the cathode, after we have the gradient of the membrane, in the cathode we have very low lambda. So we have here, for instance, depending on the operating conditions and depending on the thickness of the membrane, properties of the membrane, etc. But you can have a lambda of 2 or 1 or even lower. That means that you have, let's say, 1 molecule of water around the OH minus. So the OH minus is not solvated at all. So we don't know what happened to the OH minus, which in kind of is not a solution, it's inside the membrane, but it's not fully solvated. So we spent also a lot of time trying to see how we can simulate that, and eventually we came with an experimental method that based on non-aqueous system that we can actually generate a 0 or 0.1, almost 0, a lambda 0 environment. So we have a ultra dry non-aqueous system that we can put OH minus there at very high concentration, up to 0.5 molar, which is very difficult, but we succeed to do that. And then we can add water, so then we can simulate whatever the lambda that we want. And we found a very interesting thing. So when we follow an NMR, we follow the cation. So we use this cation, which we call standard cation, the 3-methylbenzyl cation. If we have lambda 4 or higher, meaning if you have 4 water molecules of 5 or even higher, that is fully solvated stage, this cation is completely stable. And we came back with many other cations, this is always the same. But when you have lower and lower hydration, let's say hydration of 1, lambda of 1, you can see 50% of the cation is completely destroyed in 500 hours. So what happens when you have a non-solvated OH minus, this hydroxide becomes super aggressive and then attacks by the same, for instance, for this cation, the SN2 mechanism, the same mechanism of reaction, but now the kinetics are significantly higher. And also in DFT, we calculate the energy of activation is significantly lower if you have fully solvated or you have a non-solvated OH minus. The energy of activation of the same reaction is significantly lower. Therefore, when you do not solvate well the OH minus, so the attack of this OH minus is almost immediate. And this is consistent with what happened inside the fuel cell or inside the electrolyzer. So then if you look, for instance, at those beautiful cations that are very stable in 1 molar KOH, so 1 molar KOH meaning lambda of 56, but if you test the same cation in lambda of 5, you see 100 of hours, not 1,000. And if you're testing lambda 1, you see hours for a huge degradation. This is logarithm scale, so this is a lot of degradation here. And those very stable cations in 1 molar KOH will not be stable in very low hydration number. So this is what happened in the electrochemical device. We have in the cathode low hydration number because we are consuming the water, if it is fuel cell or if it is electrolyzer, and therefore we do not have the OH minus as we know in the solution that you have many water to solvate the hydroxide. The hydroxide there is not solvated, becomes very aggressive. So that was with the cations. So we put the same cation in polymer, so now we have a polymer. So this is a PPO functionalized with TMA, so we have the same cation, and now we tested the polymer, the same reaction. So polymer at lambda 8, completely stable, more than 1,000 hours. This is what we test when we put the polymer in 1 molar KOH. So that will be very stable. So when you reduce the lambda, you can see here huge degradation lambda 4. If you have lambda 1, after a few minutes we see all the degradation and no polymer, not conducting polymer anymore. So we lose the charge here and then no conductivity. And that is the reason that the voltage going south or the current density going south in the device. So what we learn is that what as a community we do, that we want to use the membrane for alkaline device. We test the membrane 1 molar KOH. What we are doing, we are testing the membrane in very high lambda. So for instance, 1 or 6 molar of KOH, this is the lambda. in a solution. So we are simulating what happened to the membrane in the anode side of the electrode. But the problem is that the membrane, all the membrane is inside the device. So we also need to simulate what is here to try to find a method how we can find the stability here that we have low lambda, let's say from 1 to 8. And this is also what we did in the Technion once we understood that we have this gap. And again, we came back to the method that I explained before, how we measure the true OH minus conductivity. And normally, until a few years ago, we stopped the method here, and that's it, we know the conductivity. But we understood that at this point, as I explained, we have all the membrane in OH minus form. So actually, we are splitting the water, we are moving the OH minus through the membrane. This is a real device. This is what we do in the real device. We are moving the OH minus through the membrane. So if we can keep applying the current and we keep measure the conductivity, we started seeing that now we have a linear decay. So we have here bicarbonate conductivity, we apply our method through H minus conductivity, and then we have this decay, all the membranes the same. This linear decay happens because the conductivity is being losing because of the degradation of the membrane. But now this is the real degradation. This is not 1 molar KOH, because here we can set the RH, the relative humidity, we can set the temperature exactly as we have in the device. So this is a very important thing. So for instance, for the electrolyzer, we know which RH, we can simulate that in the fuel cell. The same if we work on non-aqueous solutions in redox flow batteries. We also know how many water impurities we have, so we can simulate that in this method. So for instance, using this method, so we say, okay, we have now a membrane that we produce that we believe is very stable. We found the stability during time, the stability of the conductivity during time. We set 100 RH. Indeed, this is very stable. We keep doing that for more than 500 hours, and there was no degradation at all. And again, we have a lot of water, 100% RH. Therefore, the water is enough to solvate the OH minus, not aggressive, and the membrane is good. So we are simulating what happened to the membrane in the anode side of the fuel cell or the electrolyzer. Now, what happened, the same membrane, when we reduce the RH, you can see here a very rapid degradation, and that is because we are now simulating what happened to the membrane inside the device in an environment that simulates or mimics what happened in the cathode side, that we don't have too much water. So this is very beautiful how we can see that everything. And of course, we can change also the temperature. Needless to say, all kinetics of degradation are increasing with the temperature, so the same stable membrane that is at 65 degrees Celsius will degrade very fast at 95 degrees Celsius. And this is the reason why in all the electrochemical devices, fuel cell, electrolyzer, redox flow batteries, you will see papers of researchers working on relatively low temperature and not much working at 90 or 95 degrees Celsius. That efficiency will be good, but this is because of the degradation and the instability of the anion-exchange membranes. We keep using this method, and we are now checking different cations and different backbones with the same cations. So now we are expanding and trying to understand which polymer and which cations are actually more stable for low hydration numbers. And nowadays, in a paper that will be hopefully soon published, we are examining what happened with the oxidative environment. So all what I explained before was done in nitrogen, but now we do the same in nitrogen, or 20% oxygen and nitrogen, or oxygen, pure oxygen, and you can see that as we put more oxygen, so the degradation of the membrane is much more severe, and that's very relevant, for instance, for redox flow batteries that normally we use very high potential, so it's very oxidative potential, also very relevant for water electrolyzers that we work on higher potential than in fuel cell that we work on 0.8 or 0.9 volt. This is also very relevant for redox flow batteries again, because sometimes you work in the potential depending on the redox species, sometimes even higher than the electrolyzer, so you work on potential much more higher than 1.2 volts, for instance, and then the stability of the anion-exchange membrane is also problematic with high the voltages, so we are adapting now our stability method to try to work on high voltage to have a stability method for redox flow batteries as well. Now the obvious solution also that now that we know which cations are better, so we develop new cations, and at the Technion we're working on 3 new options, and I will show just the last one. So this is the isoindolinium that we found. The isoindolinium, we don't know in advance, I must say, which cation will be more stable in low hydration number. So there was a kind of trial and error, a lot of DFT, but we were not lucky in like 10 different options, and we were lucky, I would say, in 3 options. This is one of them. Even when we thought about the isoindolinium, we found that the isoindolinium, non-modified isoindolinium, is good, but not better than the standard cation that we have. But when we modify the isoindolinium, and mainly in this way, so it's not bulky too much, but this is a very, very good stability. You can see here, this molecule is significantly much more stable, and we are testing that in 0.5 molar KOH, and very, very low hydration number. So it's completely almost no water there. And this cation seems to be very, very stable in these conditions. And the good news is that also is not better than others, but is as good as others at very high conditions, because eventually you need a membrane, one membrane inside the device. So we would like to have one functional group, although of course we can use 2 functional groups on the membrane, and that is in future one thing that we are trying to propose. Now, if you have that very high, stable, at low hydration number, so the Technion, we went to the extreme, and we wanted to try what happened when you go very high temperatures. And when I mean high temperature, higher than every other temperature that was published and was tested all around the world. And there is just 1 or 2 papers on 95 degrees Celsius showing some stability. So we went to 120 degrees Celsius. So we went over 100 degrees Celsius. And this is so far the only data that exists on an ion-exchange membrane. And we show a very, very nice conductivity, first of all. Of course, if you go to high temperatures, you have high mobility of the anions, and therefore we measure 300 millisiemens per centimeter. This is the highest ever hydroxide conductivity that was measured in an ion-exchange membranes. That actually, myself, if someone will tell me 5 years ago that we can reach that conductivity in an ion-exchange membrane, I would say, no, I don't know how to do that. And actually we are there. So there are some publications in the past weeks. I saw people reaching around 200 and even a little more. And we published this of 300, of course, at high temperature. So we run immediately to a fuel cell device, and we will be working on the electrolyzer very soon. And this is the first ever electrochemical device, fuel cell device, operated at temperature above 100 degrees Celsius with an ion-exchange membrane. As you can see, we exceed the 2 watt per square centimeter, which is very high. And the most important thing, we have a very high stability at 110. And we have been a lot of work to try to explain that stability. We don't have time to talk about that, but just very briefly, if you measure the diffusivity, as I showed before, doesn't matter at which lambda, if you go to 120 or 130, you have one order of magnitude higher water diffusivity through the membrane. And that actually helps us to hydrate the cathode. So if you have huge hydroxide diffusivity or water diffusivity, so all the water moves from the cathode to the from the anode, to the cathode, both electrolyzer or fuel cells, and that stabilizes also the cation. So we simulate all the new data at a very high temperature, and we prove also by the modeling that we can achieve better stability at higher temperature, which from a chemical point of view is counterintuitive, because normally higher temperature, higher degradation. But what happened again, because of the high water diffusivity, we hydrate more the cathode in the device, and when the cathode is more hydrated, so we gain a lot of stability as well, and that is the reason why we could go to very high temperature that nobody actually could think about that. So we are now working, and that is my last slide, working on the very special membranes that actually we understood that we need high water diffusivity. So what we do, we're using these ferrocenium cations, and under magnetic field, we are casting the membrane. So these ferrocenium cation are magnetic properties, so then we are align all the ferrocenium in the direction that we want, so from the anode to the cathode through plane. And when we have this alignment, so the water diffusivity and the conductivity is amazingly improved in the direction that we are interested of. So that's the reason that we could measure a very high conductivity for more than 4,000 hours. This is the longest ever conductivity measurement, and you can see completely stable. And now we recently also we proved this stability in 120 degrees Celsius anion-exchange membrane fuel cell, and this is the most stable fuel cell that we or anyone could do today. So that's again thanks to this all understanding how to increase the stability of the membranes. So again, those are thanks to many, and this is a partial list of the collaborators. This is another picture of our city. So the Technion is on the right here, and those are beautiful parks that you see, the German colony, the port of Haifa, my city, and the Mediterranean coast there. So those that were not being there, this is a very nice city to visit. And again, every time I say we, actually I just talk, but those are my students that they do the work. So thanks to them, and thanks to all the funding sources from different countries that actually encourage us to keep working and keep doing this work on an ion-exchange membrane. Thank you, gracias por la atención. Thank you very much. Preguntas pueden ser en español, pero I'm afraid that the answer will be in English. Yeah, sorry for that.
Thank you very much for your interesting talk. I have a question regarding the redox flow of batteries. Besides the voltage that can damage the membrane, is there any damage for the active species that are formed? In the case of flow batteries that use organic electrolytes, is there any damage caused by the radical species that are formed?
Yeah, thank you. This is a good question. So I didn't. It's a short talk. I couldn't show everything, but we recently found we did some EPR, inoperando EPR measurements with different catalysts. Although we were focusing on fuel cells, but we were working with an ion-exchange membrane. So for years, people were asking me about radicals in alkaline, and I never have an answer. Nobody has an answer until a couple of years ago. So we make this study to be able to answer that question. And unfortunately, we found radicals in both anode and cathode. It was a surprise. And now we just submit a new paper that different catalysts, not just platinum, but also PGM-free, we also have radicals. Now we work with 4 different membranes, fluorinated, an ion-exchange membrane, but fluorinated chemistries, non-fluorinated chemistry with different backbones and with different functional groups. And even after 1 month that we operate the fuel cell, we send this to my colleague doing the EPR, and we found radicals and different type of radicals in the membrane after 1 month. So now we are in progress to make, with another colleague in Switzerland, working on what happened to the functional group, meaning what happened with the membranes when we have radicals. So the first functional group, the standard one that we call, so we found that actually radicals attack, as I would say probably as expected, but we didn't know until a few months ago. So we have also a degradation for radicals. So we are expanding the method that we examine the stability, as I explained, but instead of fixed current, so we are now setting a voltage. And now we will set different voltage for different electrochemical devices. For instance, we will keep working with 0.7 or 0.8 volts for fuel cell, and that will be how we characterize the ion-exchange membrane for radicals, for this voltage, for fuel cell. And then we plan to, we started already, but we plan to submit that study for high electrochemical devices like redox flow batteries. So we just started, and we see that some functional groups, we don't know in advance which functional groups are more stable or less stable at this voltage, but some functional groups that we do not use much, but we try to use completely different chemistries, they are completely unstable at high voltage. So I expect that whenever you plan to use an ion-exchange membrane for a certain, and this is not for all redox flow batteries, that will be very important which kind of redox system and which kind of potential you plan to work with. And then we can adapt those, take those data and characterize the membranes or different membranes to see which one for that specific conditions, for that redox flow batteries, will be more stable. So the bad news in short is, yeah, the radical we have, and that will be higher potential, a higher problem. The good news is that now we have the methodology to actually mimic that conditions for different devices. So that's, I think, good. Yeah. And another point is this, but I was mentioning about the lambda, so the medium will be very important. If you work in a redox flow batteries with aqueous system, so most of the degradation that I was talking on high, on low lambda is not relevant because you will have a lot of water, but it becomes very relevant if your system is non-aqueous, and that will be more challenging, I would say. Thank you.
Thank you very much for your talk. It's very, all the subject is very fascinating. My question is about the simulations. You talked about for the study of degradation, you make all atom simulations. So you do, you study only mechanical molecular simulations, or you combine it with quantum molecular simulations?
So thanks for the question. So again, I apologize for the short time and cannot talk about everything, but we did 3 times of simulation. So all what I presented here, every time I say model, is a numerical modeling of the cell. So we have a fuel cell modeling. We are now working on the fuel model for the electrolyzer. Every time I said it was that based on that result from that numerical modeling. Now we work also on DFT, ab initio, and molecular dynamics for different topics. So for the ab initio, actually we are making very fundamental studies of the diffusivity of water and diffusivity of hydroxide and different configurations. We're working in collaboration with people from NYU in the States. For the degradation, we have some DFT and a lot of molecular dynamics. We're working with a British Columbia collaboration from there. Expertise in molecular dynamics in functional groups. So we are working about the reactivity and the proximity of the OH minus and the conductivity of the OH minus through different functional groups. And most of the DFT I didn't mention at all because this is a long other talk that we when we developed the PGM-free catalysis. So all the work theoretical work we do on electrocatalysis for both HOR and ORR are based on DFT, but I didn't show anything. My pleasure. By the way, I'm always looking for collaboration with theoreticians because theoreticians are always busy. Everyone want to work with them, and really good theoreticians are always busy. So really any new collaboration on all what I said, molecular dynamics, or ab initio, DFT, on all those topics related to alkaline systems or an ion exchange membrane, that will be really more than welcome. Thank you.
Gracias. So thank you very much for your talk. So we are working on trying to simulate here with my student Guillermo to do molecular dynamic simulations of membranes as like formed by a Nafion to see how the ions cross around it, I mean through it. So we can show you later our work. But we are at the beginning of the study, so we are still working on it. Yeah. And just the other thing that I wanted to mention is that I've been in Israel, and I think it's a very life-changing experience. So everybody, you should go to Israel.
Yeah. So thank you, and again, I am really very open to any collaboration on that. So I focus on an ion exchange membrane, but there are many phenomena, of course, that are common to all ion exchange membranes, regardless if you have cation or an ion. But any collaboration of all what you mentioned, you started doing. If you would like also to expand that for the anion exchange membrane, so I will be more than happy to sit and discuss. And if I'm not here, so discuss by Zoom and try to do something.
Thank you.
Yeah, Israel is very, very tiny, but I will do a lot of noise, so this is a really good place to visit. Yeah.
Yeah.
Thank you.
And swimming in the Dead Sea is awesome.
Okay, I see that you knew places. That's nice.
Thank you very much for your presentation. These results that you show at the end of your talk with this excessively high hydroxide conductivity, I think they are really surprising. So thank you very much. And my question is about the stability of the membranes. There are several ways to attack this issue, like changing the cationic group or cross-linking, changing the backbone, and as you showed, controlling the humidity of the membrane. So in your experience, of these many strategies that many groups have tried, what of those do you think it's like the most important that we should like focus first, and then like mainly or maybe try another ones, but the first that you would say this is the one that you should focus on?
Yeah, thank you. That's an excellent question. Unfortunately, life is a little more complicated. We cannot focus on one thing and be successful, but so the issue is that, so if you knew the literature, so as I mentioned, there are many good, stable functional groups and backbones in alkaline, but all of them, and 99% of the data is based on the famous 1 molar KOH. So you have a lot of water. Again, if you want to have a good stability in the device, so you need also to be stable for all the conditions in the device. And the device says that you have also need stability at the low hydration. So, okay, I don't know if I can be... Okay, doesn't show. So that's the problem when you have here the device. For numerical modeling, what we could find is that this is the anode, for instance, this is the cathode. And at the beginning, we understood, you prove your membrane in the device. So when we tested on the device just was good for a few hundred hours, and that's it. We take the MEA and we clean the catalyst layer, so we take the membrane and we analyze the membrane, and we always find that the membrane was stable, so we didn't understand why we have a different results in the numerical modeling. So once we have all the data of the degradation, the experimental data, we put all the degradation data, tons of numbers there inside the modeling. Now we are able to modeling the degradation inside the membrane and actually to see what happened inside the membrane. So what we found is, this is the membrane thickness here. So this is the operation at the very beginning. This is the IC, meaning how many conducting groups, how many cations you have per gram. And we saw that the membrane degrades, so this capacity of conducting OH minus degrades here in a very thin layer of the cathode, but all the membrane actually remains very stable. And that's a product of simulation, but now we can understand, because here we have a lot of water, so the membrane is stable. And actually, if you do the integral of this very thin layer, so it's like a dry skin, I call it, of the membrane, meaning you have low hydration number in that dry skin, a lot of degradation here, but all the membrane is okay. So when you do the integration of this, we found that the degradation is 3%, and that is the reason that we never saw. The 3% is like error bars, more or less. But if that 3% happen in a few micron here, so in this thin layer, you don't have conductivity at all, so your device doesn't work. It's good for the membrane. Most of the membrane is stable, but not in that thin layer. So what you must have is a good degradation for both high hydration, good stability, for both high hydration and low hydration. You cannot focus on one. And what happened is that we found that depending on the mechanism of degradation, some functional groups, like SAU, for instance, that I mentioned, is one of the, if not the most stable at high lambda. but it's terrible at low lambda. And the standard, the 3-methylbenzyl quaternarium ammonium, is relatively very stable at low lambda, but it's not good at high lambda. So you need both. So, and we don't know really in advance, and even the theoretician people that try to help us, they cannot make a million of simulation running all the cations that can exist in the world and run for this, because we don't know. We need to do tests and try to understand how we can in advance design something that will be more stable at low lambda. So what we do actually, instead of focusing on one thing, we are working on all those things that we know. So the most obvious thing, for instance, to increase the water diffusivity. So it's not related directly to the stability, but in turn it's related, because then we can move the water inside the cell, whatever the thickness of your membrane, and if you move the water much easier, so you can reach stability. So we are working with polymers, changing the polymers and designing the polymer for high water diffusivity. At the same time, we can have a membrane which is thinner. If the membrane is thinner, you can move the water much quicker as well. So you have mechanical issues. So we are working with polymers that can allow us go into thinner and thinner membranes. So we have some success on 10. Some other groups have 8 micron. This is borderline, I believe, but if you have good ideas for how to increase mechanical properties and going thinner, that's good. We need to work on cations that are more stable at both low and high hydration, like isondolinum. We're working on carbazolium now. We're working even with metallopolymers, that we found that metallopolymers actually are more stable at low hydration. Don't ask me why, I don't know. But if someone will know, please let me know. That will be really nice to know. But experimentally, this is what we found. And also, we're working on modeling, trying to see which operating conditions we can work to facilitate the more stability. So if you work on all those together, that's my approach, and also I love to do that. So if you have a little more stable in low lambda, not great, but a little more, and a little more water diffusivity, let's say water diffusion coefficient twice, not 10 times, twice. And then a little more thinner membrane and a little more better operation conditions. All together, you can jump from, and we saw that by numerical modeling, from 1,000 hours to 12,000 hours. So it's not infinite, but I can talk with Toyota and General Motors already, because those numbers, they like those numbers. So this is good enough. Sorry for the long answer, but
thank you very much.
Yeah.
Una última pregunta.
Okay, well, if there is no any other question, we want to say, thank Dr. Deckel for such a nice presentation. Thanks everyone for your attention, and we want to give you a diploma for your talk.
Diploma, wow.
Just like
Sounds
a small, like.
Very humble. Thank you very much.
And thanks everyone.
Gracias.
Gracias. Gracias.
En español, muchas gracias. my first diploma en español.
Ah, Mariano. Que dice que una foto.